Log on, tune in, find out. Another good idea from Cambridge.
Okay, can everybody hear me at the back clearly? Yes, thank you. Okay, so the problem I'm looking at today is one that I think hasn't received perhaps as much attention as it should have done in the last few years, and I'll start by setting up my problem or describing it. So the sort of design I'm looking at, I start with a plan design which I'm calling D, a binary design, an incomplete block design, V treatments, B blocks, little n observations, and treatment block incidence matrix n. And that's fine. I'm happy with my plan design, but I have the situation where I might lose some blocks during experimentation for all different sorts of reasons. There might be some sort of accident, there might be some damage. I might simply run out of resources and not be able to complete as many blocks as I've planned. So the design I end up with, my eventual design, I'm going to call D hash B star. So it's the same as my plan design, but I've lost B star blocks, and I can't anticipate in advance the size of B star or which blocks are going to be lost. So I'm interested, the biggest problem would be if D hash B star was disconnected. And by that I mean that my treatments will be separated so that some treatments are in this set of blocks and the other treatments are in that set of blocks, and I won't be able to make any comparisons between the two sets, and that will be a real disaster as far as I'm concerned. So my problem is to find conditions on the parameters of my plan design to make sure that for a reasonable size of B star I'm going to end up with a connected design. Now, the first work I found on this was by Gosh in '82. He introduced the concept of maximal robustness, and he described a binary incomplete design D as being maximally robust if you can lose any R0 minus 1 blocks and end up with a connected design. And here R0 is my minimal treatment replication. And he went on to show that balanced incomplete block designs, as you would expect, have the nice property of being maximally robust, so you can lose any R-1 blocks from a balanced incomplete block design and you still end up with a connected design. Related work was done by Baxillary and Tabis, who gave conditions on the eventual design, or on D being maximally robust, in terms of the replication numbers and in terms of the block sizes. They also gave some results in terms of lambda star, which is the smallest concurrence between a pair of treatments. Save them improved the condition on lambda star, and in work that I've done with a PhD student, Helen Warren, recently, we improved on both types of results from Baxillary and Tabis and save them. However, sadly, all of the results involving lambda star, so that's the smallest treatment concurrence, they only work if every pair of treatments occurs together in at least one block. So if your smallest treatment concurrence is 0, then none of the results on treatment concurrences will be able to tell you that your design has reasonable properties of remaining connected if you lose blocks. And that's one of the problems that I'm addressing in this work now. So, I'm going to look at two different approaches to determining how robust a design is against losing blocks in the remainder of this talk. First of all, I'm going to look at resolvable designs, and I think the approach here if you haven't come across the idea of a design being connected or disconnected before, I think it really demonstrates what we mean by design being connected and what happens when it isn't. So first result, if D is a resolvable block design and I've got R replicates and the number of blocks in the ith replicate is Si, then as long as each block in the ith replicate has a treatment in common with more than half the blocks in every other replicate, then I know that D is maximally robust. And I'm going to talk my way through the proof of this because, as I said already, it really does illustrate what happens when a design becomes disconnected. So let's think about our eventual design D hash. So we've lost any R-1 blocks. Doesn't matter which R-1 blocks. Now that means that the eventual design must contain at least one complete replicate, and there must be at least one other replicate from D that's got at most one block missing. And I'm going to call those replicates 1 and 2. Let's suppose that we have the unfortunate situation that D hash is disconnected. So that means I can separate the blocks in D hash into blocks I'm going to put in set S1, and the remaining blocks I put in set S2, and a subset of my treatments are only contained in S1, and the remaining treatments are only contained in S2. So my design is disconnected, and that will have to happen, otherwise the design is not disconnected. Then let's think about S1 and S2. Well, my first replicate obviously contains every treatment. So at least one block from the first replicate goes in set S1, and at least one block from the first replicate goes in set S2. And I'm going to suppose they're blocks 1 and 2. Now, by the condition of the theorem, block 1 has a common treatment with at least one block in what's left of replicate 2. Now think about that. Oh, and similarly S2 also has a common treatment with at least one block in what's left of replicate 2. Think about the block in what's left of replicate 2 that has at least a common treatment with block 1. Then that block in replicate 2 has common treatments with more than half the blocks in the first replicate, which tells me that set S1 contains more than half the blocks in the first replicate. Now you can use exactly the same argument with block 2, which means that set 2 also contains more than half the blocks in the first replicate. Now clearly that means my sets of blocks can't be disjoint, and therefore my eventual design D hash is connected. So that's fine. Right, what sorts of design is that result helpful in? Well, if we think about the class of affine resolvable designs introduced by Bose in the 1940s, then they satisfy the condition of that theorem. And here's an example taken from a paper by Bailey, Monod and Morgan in 95. Here we can, sorry, I didn't mean to do that. I'm trying to find the, that's it. Here I have the first replicate. I have 2 blocks of size 6, second replicate, third replicate, fourth replicate. By definition, a design is affine resolvable if you take any block and it will have the same number of treatments in common with every block in different replicates. So the first block in the first replicate has got 3 treatments in common with all the blocks in the second, third and fourth replicates. So certainly it satisfies the condition of the theorem, and it's quite easy to see by inspection. I can remove any R-1 block, so any 3 blocks from the design, and it's still connected. The lattice designs are also examples of affine resolvable designs, and so they are also maximally robust. Rectangular lattice designs also satisfy the condition of the theorem, and here's an example. I have 3 replicates this time of 12 treatments. The replicates are each occurring 4 blocks of size 3. Look at the first block of the first replicate. That has treatments in common with all but one of the blocks of the second replicate and all but one of the blocks of the last replicate. And that will be true if you look at any block of the design. So therefore, each block has a treatment in common with all but one of the blocks of every other replicate, and it satisfies the condition of the theorem because every replicate has at least will have at least 3 blocks in a regular lattice design. And that design is taken from John and Williams. So we can say that every rectangular lattice design is maximally robust. So that theorem is based simply on the definition of a design being disconnected. So we put a subset of treatments in this set of blocks and the remaining treatments in that set of blocks. What I'm going to do in the remainder of the talk is look at conditions on the concurrences between the treatments. So the concurrence matrix of my plan design is n transpose. And I'm going to have 2 definitions that I will use for following results. Think about the V choose 2 concurrences for the treatment pairs and put them in increasing order. Some of them might well be 0, some of them you would expect to be the same, but basically arrange them in order in LD. And if we have an integer m, which is between 1 and half the number of treatments, then I'm going to define lambda m as being the sum of the first m times v minus m elements of LD. In other words, it's the sum of the m times v minus m smallest concurrences. Now, if my eventual design d hash, so that's when I've lost v star blocks, is disconnected, then the concurrence matrix has got to be block diagonal. I might well need to rearrange my treatments, so I've got all treatments in one set first and then all the other treatments following, but the concurrence matrix will have to be block diagonal. What does the concurrence matrix look like for the original design? Well, I can express it as the sum of the concurrence matrix for the eventual design plus the concurrence matrix for the design made up of the blocks that have been lost, of my B star blocks. In other words, NN transpose is just N hash transpose plus NB star transpose. And writing them as partition matrices. Now here I'm assuming I only get this form if my, if my eventual design is disconnected, then N hash transpose has got to look like this. It's got to be block diagonal. And you can see that means that this part, N12, has got to be the same as N12B star. Right, what is N12? That's the part of the concurrence matrix which involves treatments from one set. So if you like, you've got your treatments here in set S1 here, and here you've got your treatments in set S2, and N12 is exactly those concurrences between one treatment in set S1 and one treatment in set S2. So when I remove the B star blocks, I'm removing all the concurrences between those two sets of treatments. And one of the things done in the work that I've done with Helen Warren is to give an improved lower bound for the smallest number of terms in N12. The larger the number of terms in N12, then the less likely, I guess, the smaller the possibility that your design will become disconnected. So in what follows, I'm going to assume that I'm going to assume two things. The second one first, I think. Because of time constraints, I'm only going to consider proper designs, so designs where all the blocks are the same size, and equi-replicate designs. The work has been done for the more general case, but the notation gets a bit messy, and the idea is the same. And the other thing I'm going to assume is that my block size is less than half the number of treatments. Because if it isn't, less than or equal to, because if it isn't, then there's absolutely no way your design is going to be disconnected, so you have absolutely nothing to worry about. So I've put that matrix equation at the top again so we can keep it in mind. So if I have a proper design, then that submatrix M12 contains at least k times v minus k terms. In other words, my smaller treatment set must have at least k treatments in it. And my bigger treatment set has at most v minus k treatments. So the sum of terms in this part of the concurrence matrix must be at least the sum of the lambda k of lambda k, which is the sum of my k times v minus k smallest concurrences. Think about what happens when we remove a block from the design. If the block contains only treatments in S1, then it won't have any impact on this part of the concurrence matrix. If the block contains only treatments from S2, again, it won't have any impact on that part of the concurrence matrix. The worst situation, by which I mean the situation leading most closely to this situation, is when you remove a block that has about the same number of treatments from each set. Now, if you have an even block size, you can have exactly half treatments from set S1 and half from set S2. And it's quite easy to demonstrate that each block contributes at most that quantity to the sum of terms in N12. Which means that if you remove B star blocks from your design, then you're removing at most that amount from the sum of the terms in N12. Now, if the maximum you remove from the sum of these terms can't be as much as lambda k, then you know your design isn't going to be disconnected and you have nothing to worry about. And rearranging that statement, that gives us this condition. A sufficient condition for D to be robust against the loss of B star blocks, it is stated there. Now that condition works even if lambda star, our smallest concurrence, is 0, which is good news. And I can demonstrate an example here. I've got a PBIB design, 3 associate classes, and you'll see that my smallest concurrence, lambda 1, is 0. So with the other conditions based on concurrences, that's a condition with Baxlari Tabis, Sathe and the work that I did with Helen Warren, we wouldn't be able to demonstrate that this design was maximally robust. But with the new condition, we can work out lambda 3, which will be the sum of 3 times 9 minus 3, the sum of the 18 smallest concurrences, and that works out to be 9. Plug that into the condition here and our block size, we get 4.5. So if 4.5 is bigger than the number of blocks that we lose, then we know the design is going to be connected. Here I've only got replication of 4, so I'm actually only interested in losing 3 blocks anyway, because obviously I could lose 4 blocks and I could lose, say, all replicates of the first treatment. So certainly that design is maximum robust. I can lose any 3 blocks and it's connected. Incidentally, I can lose any 4 blocks and I have a connected eventual design, but it might not contain all the treatments. And I'm aware I'm going to run out of time, so I will speed up a little. Right, I then actually felt quite pleased with myself because I thought I'd improved on conditions that were existing already, and I tried out the result on the group divisible designs and the triangular designs, and I was disappointed that my results weren't really better than the results got by Sathe and Satham, who had a particular condition that did look at the group divisible designs. So what I was able to do was look at the form of the PBIB2 designs in particular and replace the term lambda k by this expression. So look at the numerator, ignore the 8. Without the 8, the numerator is the smallest sum of concurrences in a rectangle in the concurrence matrix of size u times v minus u. And if the smallest of those terms, now sadly you do have to look at different values of u going from k up to v over 2, if the smallest of those terms is bigger than b star, then the design is robust against the loss of b star blocks. Now there's a term here that I haven't introduced yet, pi u. Pi u is the maximum number of pairs of first associates in a set of u treatments if your design has lambda 1 greater than lambda 2. And pi u is the smallest number of pairs of first associates if lambda 1 is less than lambda 2. How much time have I got? Okay. Right, using that formula, the specific form for pi u is quite easy to find for different types of designs. And let's look at the group divisible designs. They can be broken into 3 sets. Regular group divisible designs, now they can be further subdivided into those that have lambda 1 greater than lambda 2 and those that have lambda 1 less than lambda 2, semi-regular designs and singular designs. And it's quite easy to show with the form of pi u that every group divisible design with a lambda 1 less than lambda 2 is maximum robust. Straight away that tells us that regular group divisible designs with that property are maximum robust, and all the semi-regular group divisible designs are maximum robust. That's good. Moving on, we can also show that the singular group divisible designs are maximum robust. What I can't show is that all the regular group divisible designs with lambda 1 greater than lambda 2, I can't show that they are all maximum robust because they're not. Some of them aren't. What we can do is show that for group divisible designs with m groups of n0 treatments and lambda 1 greater than lambda 2, then the particular form of pi u is this. So n0 is the number of treatments in each of my groups in my PBIB2, and u, the number of treatments I'm interested in. So I'm looking at a u times v minus u submatrix of my concurrence matrix. I can write that as gamma n0 plus delta, and that gives me this form for pi u. If I plug that into my condition for the PBIB2s, then that's a condition for robustness against the loss of any B star blocks. Using that condition, I can look at all the designs in Clatworthy that are group divisible designs with lambda 1 bigger than lambda 2, and in each case I have identified the maximum number of blocks that you can remove to still have a connected design. and that's improved on what Southern and Southern were able to do. In some cases it's picked up some errors that they've made as well, and I think what they did was very good, but this has improved on that. I'm currently looking at the designs, the PBIB2 to the triangular association scheme in the same way, but I think that's it. Right, those are important works. Well, some have got designs that I've used, and other papers are important work in the area. Right, thank you very much.
Are there any questions for the speaker? Rosemary?
You did show us one partially balanced design with 3 associate classes. Do you recall what's the association scheme there?
No, all I knew was it was PBIB3.
Okay, so perhaps I'll look at it later.
Yeah, you probably know more about that than me. Yeah.
One other question?
I wondered, this might be for the future, whether it's possible to build in your conditions into classes of new construction methods for designs, and then maybe you will generate a lot of competing designs that do well on robustness, and you could perhaps choose between those on grounds of efficiency if all goes well.
Yes, no, I'd like to do that. And also I think even though it might be that you think you've got nothing to worry about because you'd have to lose so many blocks before it became disconnected, I think as it approaches becoming disconnected, some of your treatment contrasts are going to have large variances. So you'd want to, so that gives you more motivation as well. Yeah, thank you.
Perhaps another question? No, then let's thank the speaker again.